In this screencast, we'll talk about electric fields. In the previous section, we were finding the force between two charges. We could use Coulomb's law to do that. We did some problems where we had more charges, and you saw that it could get quite complicated trying to find all these forces and add all these vectors together. We did it for 3 charges. You could imagine if it gets up to 10 or 1,000 or a billion charges, this problem would get very, very difficult. So in order to represent the effect of a large distribution of charges, we have something that's called the electric field. So today we're going to see just what is an electric field, how charge and electric field and forces are related, how we can represent electric fields in diagrams and other models, and what you can use, how you can use an electric field. So electric field is a property of the space around a charged object. The fact that this charged object will introduce forces on another charge, this is the way that you're able to measure the effect of an electric field. In figure 1, we see something called a plasma globe. This is an object that has charged particles inside of it. There's an electric field from the charge in the center of the sphere. The forces from that charge will push the charged particles in the plasma out toward the side of the globe, thus creating an effect where we're able to see the effects of the electric field. Now, to measure an electric field, what we do is we take a small charge, take a test charge. In this case, we are calling this a Q prime, the small charge, put it at different places around a charge that is creating the electric field. What you'll see is that the charges interact with each other. There'll be a force on that charge. For measuring the force on this test charge, we can find something that is called the electric field. The strength of an electric field is equal to the force on the charge divided by the amount of the test charge itself. This is the definition of electric field. It is measured in units of newtons per coulomb for force per charge. So as you can see here in figure 2, in this particular case, we have the charge in red. This is the charge that is creating the electric field. The small charge in different locations around that red charge is going to feel a force that is radiating away from that charge. Based on this, we would be able to draw diagrams of electric field, which I'll show you in a little while. Now, make sure if you're going to do these measurements, the test charge needs to be very small. We want to make sure that it does not affect the distribution of the other charges. We want to make sure its effect on the main charge is negligible. You can measure the strength of an electric field. You can use Coulomb's law to calculate the strength of an electric field only in one circumstance. Now be very careful. I've seen problems on tests where people go equation fishing. They see an equation and say, oh, this is the equation I'm going to use. Now this equation down below here, we say that it's always true that the electric field is equal to the force divided by the charge. If and only if the charge is a point charge or it's a uniformly charged sphere, then we can use Coulomb's law to calculate the strength of the electric field. In that case, it would be the Coulomb's law constant times the charge divided by the distance squared, the distance away from the charge. So this would be true, just like with Coulomb's law, the further away you are from a charge, the weaker the electric field would be. Now we can develop models of the electric field. In figure 3, you see that if we have a positive charge, the electric field lines will radiate away from that charge. Anywhere you'd put a positive test charge in here, they would feel a force that points away from that center charge. So these field lines, these are diagrams to show what the direction of the force would be on that positive test charge. If instead we had a negative charge, then the field lines would all point in toward that charge. And as a matter of convention, if there are more lines, if they're drawn in more densely, that indicates a stronger electric field. You can also have a mix of charges. You could have a combination of positive and negative charges. In this case, electric field lines always point away from the positive charges and point toward the negative charges. Now, it's important to recognize that electric fields really exist in 3 dimensions. Any picture you draw on the paper is just going to be a 2-dimensional representation of it. We'll just see those field lines that exist in the plane of the paper. So there are a few cases here. We have some examples of pictures using different materials where you can see the effects of electric field lines. If we have 2 charges, you can see, in this case, a positive and negative charge. You can see the field lines going away from the positive charge toward the negative charge. If we have 2 positive charges, in the center, right in between them, you notice that the vector sum of the forces would cancel out. There's 0 electric field right there in the center. So with this information, you will be able to answer all the questions in the launch homework and continue your exploration of electric fields. So read the chapter and answer the questions.